who will talk about amplitude tuning of steady-state entanglement in strongly different qubits.
Okay. Okay, good morning, everybody. Thanks for the invitation. I'm going to switch a little bit the subject, but not too much. So I'm going to tell you about a new proposal to generate steady-state entanglement in strongly driven dissipative systems. I'm going to focus on flux qubits, but our proposal could be extended to other, at least solid-state devices. So the usual way to generate entanglement, as you might know, is through unitary evolutions, unitary transformations, or even through adiabatic quantum computation in order to drive the system to the ground state with its entangle. But in the recent years, there's new proposals that take into account that actual systems are open systems that are in contact with a thermal bath. So there are new schemes to profit from this environment to make some engineering of the bath in order to, for example, adapt the decay rates between the system and the bath in order to drive the system to a steady state that is a target entangled state. And most of these schemes relate on the fact that the system is an open system and profit for some driving fields in order to induce and select the desired transitions to reach these ground states. These schemes have been realized in many, many systems in the last these 10 years. We have proposals with Trump ions, it's in the David Weiner group also, in which they can select this singlet state by applying different pulses, lasers to the systems, and to select the desired transitions in order to that the population of this singlet state is the largest one, so to have a steady state entanglement as a function of time. There are other proposals in atomic systems, also in atoms in optical cavities. All these proposals rely on the fact that we have driving fields, we have open systems, and they select some symmetries of the bath. There's some symmetries of the system also to select the target entangled states. There are also proposals in superconducting qubits, in solid-state devices, in transmons, in cavity qubit proposals, in which we have, for example, here, they have two qubits, coupled qubits to the same cavity. In this proposal by the Siddiqui group, they have the two coupled qubits coupled each one to different cavities, so they can profit from some symmetries of the bath in order to select some state, to generate dark states, so that the entangled state could be a dark state for this kind of protocols. So in all these schemes, the idea is to induce transitions to drive the system to the desired entangled state by applying laser fields, driving the system, or either the bath, the cavity, in the case of, for example, cavity QED, in a way to engineer the system and the bath coupling and select, as I said, the entangled steady state. But these approaches rely essentially on applying resonant drivings and in generally weak drivings. And so the formal treatment of these dynamics and the evolutions relied on the rotating wave approximation in which the driving fields are resonant with the select transitions to the steady state entanglement. So the idea of our proposal is to induce dissipative steady state entanglement by applying strong driving fields beyond these usual rotating wave approximations. So we are going to focus on strong, what I mean by strong is large amplitude driving fields that are not necessarily resonant with given transitions. And we're going to test our proposal in superconducting flux qubits driven by microwave fields. So these strong driving protocols had been applied in the last year in superconducting flux qubits and even in solid state and charged qubits also. A new interesting phenomena emerged beyond the weak amplitude regime. There's a new kind of interferometry that can be performed on these qubits by exploiting the fact that large amplitude fields are applied, and also new phenomena, for example, the population inversion in the flux qubit state mediated by the bath. These new phenomena have been actually investigated in the last year in these flux qubits driven by microwave fields. For those of you that are not familiar with the superconducting qubits, I'm going to focus in flux qubits. That doesn't matter a lot the details, but these two superconducting qubits are coupled, generally can be coupled by some capacitance or some inductance. I'm going to focus in two flux qubits that are coupled inductively, and many devices are shown here from different groups, Delft, MIT, that work with these flux qubits that are capacitively coupled. So the model for the two qubits is the following. We have two qubits. In the case of the qubit, each qubit is characterized by two main parameters. One is related to the applied DC flux in each qubit, and the other parameter is something that is settled by the experiment, by the superconducting junction and for the charging energy. But for the purpose of this talk, this parameter is going to be fixed. And this is a parameter that can be tuned because it's related to, as I say, the DC flux that is applied to each qubit. So as I say, these two qubits are going to be coupled capacitively, which in this case means that we have this kind of interaction between the two qubits, which is transversal to this sigma z component. And on top of this, these two qubits are going to be subjected to a time-dependent harmonic microwave field. So I'm going to model this time-dependent harmonic flux by this amplitude A, and this is the frequency of the harmonic flux that is applied to each of the qubits. We are going to consider specific case in which it's the same flux that is applied to both qubits, but the flux could be even different. So this is the way to mimic this usual driving in the microwave field that the experimentalists are used to apply to the qubits. So as I said, the system is an open system. There is an environment in which the system is in contact with the circuit, the electromagnetic environment. So the truly dynamics of the system is an open system. It's not a closed system. So we are going to consider this fact by introducing coupling to a bath. The bath is a usual bath of harmonic oscillators. I'm going to consider some spectral density which corresponds to an ohmic bath, but another spectral densities can be also considered. And the typical coupling in the case of qubit is through flux fluctuations. So in the case of flux qubits, the coupling between the system of the bath goes through this operator that is related to the sigma C matrices, which are the matrices that is related to the flux. So as I said, we have an open system, but on top of this, we have a system whose Hamiltonian is periodic in time because the system is subjected to these AC microwave fields. So in order to solve the dynamic of a time-dependent periodic systems, the usual way to do it is by the Floquet theory. I'm not going to enter in the details, but from those of you who are familiar with this is the usual way to solve time-dependent harmonic Hamiltonians. So instead of having eigenenergy, we have the Floquet state, and in eigenfunctions, we have the Floquet states. Instead of having eigenenergy, we have quasi-energies. Okay. So our matter of study is density, the reduced density matrix of the system, which is a trace over the total density matrix. We're going to compute this reduced density matrix in the Floquet basis. The Floquet basis is a preferred basis to analyze the dynamic of open and driven systems, because diagonal density matrix in the Floquet basis is almost diagonal in the steady state. And this is something that happened for the Floquet basis and not for the, for example, vectors basis. So to solve the dynamics, we use this kind of master equation, but in the Floquet basis and in the Born approximation. So this is called the Floquet-Born-Markov equation. And in these terms here, all the decay processes are hidden, okay? So this is the operator that takes into account all the relaxation processes that happen in the system. So in the steady state, this term is 0, so we can, by diagonalization of this operator L, we can access to the decay rates of the system in the presence of driving, okay? This is very important. So our system, as I said, I'm going to focus in the case of the undriven situation, the Hamiltonian, this coupled 2 qubit Hamiltonian can be mostly obtain the eigenstate almost analytically, and this is the energy spectrum as a function of this quantity, what is the flux, essentially, the flux detuning, okay? And as you can see, we have 4 kinds of state. We have 2 coupled qubits, we have 2 states. The ground state is entangled for these values of flux detuning, but then it's a separable state. This is this state, 0, 0. We have 2 entangled states, and we have another separate state. So there are the 4 states, and these are the energies of of each of these states. And as you see, this energy goes with the flux detuning for the low ground state and the upper state, and they are insensitive to the flux for the 2 entangled states. So when the driving is put on top of this is the autonomous, energy spectrum. When the driving is put on top of this, I'm going to focus in the emergency of resonances in the system. Of course, the condition of resonances is each time the difference between 2 of this energy is a multiple of the applied frequency. So we can distinguish 3 kinds of resonances. Resonances between 2 separable states, that if you see the difference here, goes like a multiple of the frequency. We have a resonances between a separable and entangled state, which is a resonances that depends on the flux detuning and on the J coupling constant. This J coupling constant in this case is a fix. It came with the experimental setup. I'm not going to touch this. In the experiment, we can design different coupling constant, but this is settled by the experiment. And we have this kind of resonances between 2 entangled states that are resonances that also take place each time the coupling constant is a multiple of the driven frequencies. As an entanglement measure, I am going to take the concurrence, because the concurrence is something that can be accessible experimentally by performing tomography of the density matrix. So, as you might all know, I'm going to focus that for this full entangled state, the concurrence is 1 and 0 for separable states. This is here. We show some experiment in the CDK grouping with the concurrence by measuring tomography of the density matrix in the case of 2 coupled flux qubits. So let us start for the easy situation. I'm going to prepare my system in the ground state, okay? And I'm going to compute the concurrence. First, of course, if in the absence of driving, I can plot the concurrence as a function of the detuning and this J coupling constant, okay? So if you see for this value of J coupling constant, the spectrum, as I said, the state is entangled for, detuning, which is smaller than half of the coupling constant. So this region only is it's reproduce the fact that I have entangled state, ground state for this value of the tuning, and for other values of the tuning, this ground state is separable. So this picture says nothing more than this spectra, okay? But what happened in the case of the unitary dynamics when I turn on the driving? What happens? What happens is that, you know, some here, there are the resonances, okay? As I mentioned, these are the resonances, and I say that some entanglement is created along these resonances regions, okay? So these are the resonances that goes linearly with, you know, with J, okay? This corresponds to resonances between separable and entangled states. I have resonances between entangled and entangled state that are these vertical lines, and I here also show resonances between two separable states that are the straight lines here. So on the resonances, some entanglement is created, okay? So there are particular places in which entanglement is created. You know, the scale here. We transform these black regions in some region with color, so entanglement is created on the positions on the resonances. But this is for the unitary dynamics. As I said, I'm interested in the open system evolution, so I'm going to compute the concurrence for the steady state situation. So, as I said, we start for the ground state, which is for this value of the tuning, could be either, I mean, entanglement or separable. This is the picture I showed before for the unitary evolution, and you can observe a dramatic change in the concurrence computed for the unitary evolution or for the open system evolution. This is a map of the concurrence in the steady state, okay, after full relaxation of the system. And as you see, you have creation of entanglement, okay, near and close to the position of the resonances, not exactly at the position of the resonances, but the map changed completely. And also you observe regions in which entanglement is completely destroyed, okay? So the steady state concurrence, it's very different from the unitary evolution dynamics for the concurrence computed for the unitary evolution dynamics. So keep in mind that we have rich behavior close and near to resonances, and the resonances, as I said before, are this one, this one that I mentioned before. So we have creation, death, and revival of entanglement. So how we can understand this behavior of the concurrence? So I'm going to focus on three different kind of resonances, as you see now, the resonance between separable and entangled state, which is, this is black, and I prepared the initial state is, in all the cases, is the ground state, which is separable, and I see how the evolution of the density matrix, the diagonal density matrix elements, behaves as a function of time. So in these three cases that correspond each case to select the flux detuning corresponding to the different resonances. So we can select with the flux the different position of the resonances. We evolve the system. We start with the ground state in this situation, in this situation, in this situation, and let's evolve the system and see what happens in the stationary steady state. So as I said, in all the three cases, we have for short time dynamics below the, the coherence time, we have this rabbit-like behavior, which is typically to the case in which we have selected different resonances. We have the superposition of this state, and this superposition creates a sort of entanglement and concurrence for the short time dynamics. We see a striking different behavior for large time dynamics above the coherence time, okay? We have that in this case, we have the destruction of the entanglement, the concurrence goes through zero, but we observe that some creation of entanglement take place for the case of these two resonances between separable and entangled state, okay? So these resonances here correspond to these resonances between two separable states, but it's really close to the resonances between the separable and entangled state. And this is going to be important, okay? So the creation of concurrence happens near the positions of the resonances between a separable and an entangled state. So we can study the time evolution of the concurrence. As I said, I'm going to focus in these two positions of the, I'm going to consider an initial state with a close but not in resonances, and a system position in the flux detuning, which is resonances between two separable states, but these resonances is very close to these other resonances here between the separable and the entangled state. So I'm going to consider here this plot corresponds to this resonance, that is determined by the value of the flux detuning. As I said, here is a plot of the concurrence as a function of time. And as you see, we have initially, you don't see any creation of concurrence because we are not in the resonant condition. But at large time scale, you observe the creation of entanglement, okay? In this situation, it's different. We are initially at a resonance, okay? So we observe these fringes that are these fringes that are related to the short time entanglement creation by the resonances. But in both cases, what we see is that for large time scale, we have population inversion, okay? For large time scale, the density matrix is dominated by the weight is on the entangled state, okay? So the idea is to try to explain why. So we have population inversion. The first excited state is populated, okay? The first excited state is an entangled state. And this population, the inversion of population and the population of this state dictates the fact that we have an increase in the concurrence for large time scale. So the idea is how we can understand this population inversion that leads to the creation of concurrence for large time scale. So the short time dynamics in both cases is different, okay? But the large time dynamics in both cases shows the creation of entanglement. And what is nice is that this can be controlled by the amplitude of the driving, okay? In these two cases, I fix the amplitude of the driving to this value in units of the frequency of the driving. But here I'm showing a plot of this steady state concurrence as a function of the amplitude of the driving. So by tuning the amplitude of the driving, you can create a region in which entanglement is enlarged, okay? Concurrence reach larger values. So to sum up the two results, we can modulate the concurrence, the steady state entanglement, by selecting which is the flux detuning and which is the amplitude of the driving. So in the steady state, we generate regions in which the concurrence is enlarged. So how we can understand this behavior? So we have an open system. All the idea is that we have the decay rates. The decay rates, of course, are related to the bath, spectral density of the bath, which in this case we have this operator that is related to the sigma C Pauli matrices, but the operator that is of the bath that is coupled to, the operator of the system that is coupled to the bath, okay? But what's important is here. In the case of the driven system with the amplitude of the driving goes to 0, we have only one relaxation channel, okay? The usual relaxation channel for an open system without driving. When we have driving, we have additional relaxation channels that are related to the fact that the system can be absorbed or emit photons, okay? And we have channels that are related, or decay rates that are related to processes that take into account the absorption or emission of a number of photons. And these relaxation rates can be almost, compute in a quasi-analytical way, but as a sort of Bessel functions-like behavior. So we can modulate the relaxations rate in the presence of driving with the amplitude of the driving. This is the idea. So for example, as I show you, we have to obtain a steady state entanglement, we have population inversion. So in a way, we have to select these decay rates in order to populate this state. you know, if you don't have driving, it's impossible to populate the first excited state if you start from the ground state at almost 0 temperature, okay? But in this case, what happened is that by the driving, by the amplitude of the driving, we can make some of these decay rates that involve the absorption of a number of photons in order to populate the first entangled excited state. So, for example, in this case, close to these resonances, I have these processes. I start for the ground state, and you know, you can the system can absorb 1, 2, 3 photons, okay, and then decay, okay, to the first excited state. This is the idea behind this process to control with the amplitude of the driving close to a resonance. We can move close to a resonance in order to select, for example, this decay rate. So as you see, this can be, I mean, we have a range of amplitude in which for a small time scale, we don't have entanglement, but we can create entanglement, okay, at the steady state. As I say, this, for example, is, I'm showing here the 2 decay rate. This is the 0 decay rate, which is the decay rate in the absence of driving. And when we have this phenomena of population inversion and enhancement of the entanglement, we see what this is the decay rates that dominates, okay? So this can be also, we can fix the detuning, and you see that we can select different regions of the amplitude of the driving in order to modulate the concurrence, okay? And in each of these regions in which the concurrence is enlarged, we have this phenomena of population inversion in which we have the density metric that is dominated by this entangled first excited state. So we have this time evolution of the concurrence. As I said, we have a short time dynamics below the coherence time in which the concurrence evolves like a unitary system. We have an intermediate dynamic state in which, I mean, we have some destruction or revival of the concurrence, and the large time dynamic would take place after full relaxation of the system with the bath. Also, here are maps as a function of the detuning and the amplitude for these 3 different time scales, and you see how these maps change as a function of time. So to conclude, what I try to show to you is that we can we propose a new mechanism in order to control entanglement in driven dissipative system, and the control and the generation of entanglement is essentially dominated by the large amplitude driving that we are applying to the system. And we have observed the rich dynamical behavior of the concurrence of the entanglement as a function of time, with the creation, revival, and also death of entanglement. And what I say, this proposal can be applied to other solid-state devices. In the case of coupled double quantum dots, there are also this protocol of Landau-Zehner-Stueckelberg spectroscopy that have been applied. So there are systems that beyond, I mean, superconducting qubits can be studied to analyze these new mechanisms to generate entanglement in the steady state. And with this, I would like to thank my collaborator. This is Anna, my student, and Daniel, my long state collaborator, and Alejandro Ferrón, that had been collaborating in the early stage of this project. And this is not Córdoba, this is Bariloche. Okay? And well, thanks you for your attention.
Questions?